Hi everyone, I'm Francis Gracy dual doctoral student of University of Tartu and Ben Gurion University of the Negev. In this video, I and my team members Agnes and Shiva will present our recent research work on Fresnel incoherent correlation holography. Fresnel incoherent correlation holography, abbreviated as FINCH, was developed by Professor Rosen and Professor Brooker in 2007. FINCH was one of the first demonstrations of incoherent digital holography using an SLM for 3D imaging application. In FINCH, every object point is converted into two beams, spherical and plane waves or two spherical waves, and interfere to create a self-interference hologram. Since the object is illuminated by a spatially incoherent light, the interference only occurs as self-interference with no mutual interference. FINCH attracted a lot of attention during the time of its invention, mainly due to its ability to break the Lagrange invariant condition and achieve a super resolution of about 1.5 times that of an incoherent imaging system with the same numerical aperture. However, FINCH also had certain disadvantages. That is, FINCH inline configuration requires at least 3 self-interference holograms with 3 relative phase shifts, that is theta equals 0, 2 pi by 3 and 4 pi by 3. This requirement reduces the temporal resolution of FINCH by 1/3 that of regular incoherent imaging system. FINCH has a lower axial resolution than regular incoherent imaging system, and FINCH has a low light throughput as the FINCH hologram is generated using either spatial random multiplexing or polarization multiplexing, which reduces the light throughput to about 25% of input light. Recently, FINCH was implemented as coded aperture imaging, abbreviated as CI system, where only single FINCH hologram of an object was recorded and processed with the point spread hologram library, that is pre-recorded only once to reconstruct the 3D information. However, the signal to noise ratio was not high.
In this research work, once again, FINCH has been implemented as CI but with many advanced computational algorithms. A recently developed computational algorithm, Lucy-Richardson-Rosen algorithm, was used for image reconstruction with high SNR. Lucy-Richardson-Rosen algorithm has been discussed in many of our talks from CIPHR group in the past. I summarized the algorithm here. We need to reconstruct the image of the object IR from the object intensity IOH and the point spread function IPSH. The LR consists of a forward convolution between the approximate solution and the PSH, and the backward nonlinear reconstruction. This algorithm begins with an approximate solution IOH, which is the closest to the object information, yet a distorted version of object. In the first step, IOH and IPSH are convolved to obtain the object intensity IOH prime. In the next step, the ratio between the original object intensity IOH and obtained object intensity IOH prime is calculated. This ratio is correlated with IPSH using NLR, and the result is called the residue. This residue is multiplied with the previous solution, which is IOH in the first iteration and IR power P after the pth iteration. The result gradually moves from IOH towards O with every iteration until an optimal reconstruction is obtained. From our previous studies, it is established that LRRA has a better performance than matched filter, phase-only filter, and nonlinear reconstruction.
A recently developed phase mask design method called as transport of amplitude into phase based on Gergbeck section algorithm TAP-GSA for improving the light throughput of FINCH. SLM technology is limited to display of either phase-only or amplitude-only information but not complex information. However, when two or more phase functions are summed, a complex function is obtained, which is not possible to display in an SLM. Therefore, alternative methods such as random spatial multiplexing and polarization multiplexing methods were developed to display multiple masks simultaneously at the expense of low light efficiency. We present a recently developed algorithm called as transport of amplitude into phase based on Gergbeck section algorithm. In this algorithm, the magnitude of the complex function is transferred into the phase to obtain a phase-only function which is equivalent of a complex function with a high light throughput close to 200%. This is used to improve the light efficiency of FINCH. This algorithm consists of 2 steps. In the first steps, 2 or more pure phase functions are added resulting in a complex function. Here, two pure phase functions named DOE1 and DOE2 are used. The resulting complex function is numerically propagated from the mask plane using a Fresnel transform to the sensor plane, and the resulting complex amplitude is the ideal function at the sensor plane. The tab GSA begins at the mask plane with a uniform amplitude and a phase extracted from the phase of an ideal complex function. The resulting complex amplitude at the mask plane is propagated to the sensor plane using a Fresnel transform, and the resulting amplitude is replaced by the ideal amplitude calculated at the sensor plane for the ideal complex function at the mask plane. The resulting phase after the Fresnel transform is partly replaced by the ideal phase. The ratio between number of pixels replaced to a total number of pixels in a matrix is the degree of freedom. This process is iterated until the phase function in the mask plane converges to an optimal one. Here, the holograms of the pinhole with the same exposure time of 1587.4 milliseconds were recorded for polarization multiplexing, random multiplexing, and spatial multiplexing with tab GSA. As shown in the figures, the power requirements of polarization multiplexing and random multiplexing are higher than those of the proposed tab GSA method.
Finally, a PSF engineering method is used to remove the resolution constraint of Chi systems. In Chi systems, it is impossible to resolve features beyond the size of the pinhole. But with PSF engineering method, it is possible to surpass the limit. Chi is applied to FINCH, but Chi has its own problem, a secondary bottleneck in resolution in addition to the primary bottleneck, which is the numerical aperture, NA. If the pinhole used for recording the PSF is smaller than the diffraction limited spot size imposed by the NA, then there is no problem. But in practical scenarios, it is not possible as the small pinhole allows only few photons and the intensity drops close to the noise level of the image sensor. Therefore, in most experiments, the pinhole size is larger than the diffraction limited spot size imposed by the NA. This reduces the resolution of the imaging. So, how to solve this problem? We use the same method, but instead of doing reconstruction in a single step, we break it into two steps. In the first step, we record PSH with a pinhole and then record a direct image of the same pinhole. From these two recordings, we synthesize a new PSH, which we call the ideal PSH. This ideal PSH, when processed with a recorded object intensity pattern, the resulting reconstruction has features resolved beyond the size of the pinhole. Next, experimental results for obtaining an ideal PSH from the recorded PSH is shown. The ideal PSH was engineered from the recorded PSH using the direct image of the pinhole. Here, figure A shows the recorded PSH, figure B is the engineered ideal PSH, and figure C is the recorded OH. Row 2 shows the reconstruction results of recorded PSH in figure D and engineered ideal PSH in figure E and direct imaging in figure F. It is observed that the result obtained from engineered ideal PSH looks sharper. A simulation study was carried out in MATLAB for conventional FINCH and FINCH-SCHI. The logo of the University of Tartu was used as the test object shown in figure A. The first row shows the FINCH holograms with 3 phase shifts, that is theta equals 0, 120, 240. Displayed in figure B, C and D, which are then superposed to form a complex hologram whose amplitude and phase and its reconstruction are shown in figure E, F and G respectively. The direct imaging result is shown in figure H. Comparing the reconstructed image with the direct image, an improvement in lateral resolution is observed for FINCH. Third row shows the results for FINCH-SCHI. The phase mask created using tab GSA is displayed in figure I, recorded point spread hologram in figure J, and object hologram in figure K, and reconstruction using LR array is shown in figure L. The axial characteristics were investigated. The normalized intensity value of the reconstructed point object is plotted against the axial distance error. The direct imaging is given in blue color and conventional FINCH is dotted red and FINCH-SCHI is dotted yellow. It is clear from the plots that FINCH, when implemented as SCHI, has a higher axial resolution than conventional FINCH. Then, a simulation study was carried out for engineering ideal PSH. In row 1, the USAF 1951 test object is shown in figure A, PSF with a diameter of 60 micrometer in figure B, object hologram in figure C and its reconstruction in figure D. In row 2, the PSF with diameter 400 micrometer and its reconstruction is shown in figure E and F. An engineered ideal PSH obtained from PSF with diameter 400 micrometer and its reconstruction is shown in figure G and H. It is seen that there is some loss of information and distortion, but the higher resolution inherent in FINCH is preserved.
This is the optical experimental setup that we used for this research work. In this, the light emitted from the high power LED shown in element 1 entered the setup. A refractive lens L1 shown in element 5 with a focal length of 10 cm was used to collimate the light from the diffuser shown in element 4. A polarizer shown in element 6 was used to polarize the light along the active axis of the SLM. The light from the polarizer entered the another refractive lens L2 shown in element 7 with a focal length of 5 cm which critically illuminated the object. The light from the object shown in element 8 was collimated using another refractive lens L3 shown in element 9 with a focal length of 5 cm and it was placed at a distance of ZS 5 cm from the object. The collimated light entered the beam splitter shown in element 11 and reached the SLM shown in element 12. The phase shifted masks synthesized using TabGSA algorithm were displayed on the SLM and the FINCH holograms were recorded by the image sensor shown in element 13 placed at the distance of ZH 21 cm from the SLM.
These are the experimental results for single plane imaging, which was carried out to compare the SNR and RMSE between the conventional FINCH with 3 camera shots and FINCH sky. The digit 1 from group 5 is used for the study. Row 1 shows the conventional FINCH approach. The face masks are obtained from the TabGSA are shown in figure A, B and C, and the phase shifted holograms in the figure D, E, F. Row 2 shows the superposed magnitude in figure G and the phase in figure H, and its reconstruction in figure I. The FINCH as sky results of the recorded IPSH and IOH is shown in figure J and K. The direct imaging results are shown in figure L. These are the plots for the SSIM and RMSE values for the conventional FINCH and FINCH sky in figure M and N. As we observe from this plot, the performance of FINCH as sky has been significantly improved. These are the experimental results for 3D imaging. Here, the axial resolution of FINCH as sky has been compared with the conventional FINCH by a 3D imaging experiment. The 2 test objects of digit 1 and digit 3 are used. These are the recorded FINCH holograms as you can see from figure A, B and C, and magnitude in figure D and phase in figure E, and their reconstruction results in figure F. Here, the PSH are recorded for the 2 planes in figure G and H and their corresponding holograms in figure I, and the reconstruction results are shown in figure J and K. On comparing the results, the axial resolution is improved in our approach. Both objects are focused in conventional FINCH, whereas only one of the 2 objects are focused in case of FINCH as sky.
In this research, FINCH was improved along many axes simultaneously: temporal resolution, axial resolution and signal-to-noise ratio. Then PSF engineering approach developed for FINCH sky will benefit all coded aperture imaging methods. We hope that the new possibilities presented in this study will lead to the development of improved FINCH scopes in the future. We thank Professor Vijay, Professor Solius, Mr. Aravind Simon for their valuable contribution. Thank you for watching.